All right. When the first derivative is positive, what does that tell you about the function? It's increasing. When the first derivative is negative, what does that tell you about the function? It's decreasing. When the first derivative equals 0, what does that tell you? It's a possible extreme value. It's a critical number. When the first derivative does not exist, what's that tell you? It's a possible extreme value. It's a critical number. The only time a function can change from increasing to decreasing or decreasing to increasing is when its derivative changes sign. And the only place a derivative can change sign is when the derivative equals 0 or the derivative does not exist. Okay? Now you've got to understand that relationship, and you've got to remember that relationship. We talked about strictly monotonic. Many functions are not actually strictly monotonic. However, all functions can be divided up into intervals so that they are. Okay? So that's why critical numbers are critical. Right? That name's not an accident. They're critical because that's where the direction change can occur. That's the only place the direction change can occur. Okay? The only time a function can go from going up to going down or vice versa is at the point where the derivative equals 0 or the derivative does not exist. That's the only two places that can possibly happen. So that means that in between critical numbers, the function's always strictly monotonic in between critical numbers. It's always either increasing or it's always decreasing, one of the two. So that's why when we're doing the first derivative test to find extrema, we find the critical numbers. That tells us, well, then we find whether or not the derivative's positive or negative in between those critical numbers. That tells us where our extrema occur. Okay? Now, we use the same idea on things like number 62 here. All right? We're not going to have, we're not going to have the equation for the derivative or for the function. We just have to use the concepts: function increasing, derivative positive; function decreasing, derivative negative. Function can't change directions unless the derivative equals 0 or does not exist. We're going to use those concepts to either be given f and figure out things about f prime, or in the case of 62, be given f prime and figure out things about f. Okay? So take a look at number 62. It says, use the graph of f prime to identify the intervals on which f is increasing or decreasing and estimate the values of x at which f has a relative maximum or minimum. So if you look at the graph of f prime, this is not the graph of f, this is the graph of the derivative of f. Notice that at first, so from negative infinity to somewhere, what's the sign of the derivative? Positive or negative? It's positive. Okay, so from negative infinity to what sure appears to be negative 1, the derivative is positive, therefore f is increasing. Okay, so from negative infinity to negative 1, f is increasing. Now, at negative 1, the derivative is 0, isn't it? Right there, that point right there, the derivative is 0. The y-coordinate of the derivative is 0. So when x equals negative 1, the derivative equals 0. So that's a critical number there at negative 1. That means the function, if it's going to change directions, that's where it's going to change directions. So let's figure out what direction the function's going from negative 1 to, and then the derivative stays negative, so So what's going on from -1 to infinity? The derivative is negative, so what's the function doing? Decreasing. So we've done part A. We identified the intervals where f is increasing or decreasing. Okay? Now, since the derivative went from negative to positive, no, I said that backwards, didn't I? Since the derivative went from positive to negative, our function went from increasing to decreasing. When the derivative switches from positive to negative, is that a relative max or a relative min? That's a relative max. So we know that f of -1 is a relative max. We have absolutely no way of knowing what the value of f of -1 is. They don't give us any clue about that at all. Now, if you understand and you remember that when the derivative is positive, the function is increasing, and when the derivative is negative, the function is decreasing, that's just a gimme question. It really is. Now, unfortunately, probably the majority of you were looking at me like I had three heads because you were looking at the graph and you were being distracted by the direction the derivative was going. If the derivative is decreasing, that has nothing to do with whether or not the f is increasing or decreasing. It's the sign of the derivative. So look, isn't everything above the x-axis positive? So when the derivative is above the x-axis, it's positive. I don't care if it's increasing or decreasing. I care about the sign of the derivative. So there in the blue, the derivative's positive. So from -infinity to -1, the derivative's positive. I don't care that the derivative's decreasing. I don't mind that. That doesn't have anything to do with it. Okay? Since the derivative is positive, f is increasing. And then look, everything below the x-axis is negative. So everything there in red, the derivative is negative. And when the derivative is negative, f is decreasing. Okay? That's what you got to start looking for, isn't it? You need to start looking for where does the derivative cross the x-axis. Because that's your clue. Okay, does that make sense to you? That's what you got to start looking for. So look, if I did, let me just make one up. And all I'm going to put on here is the x-axis. Here's the x-axis. Okay? I'm not even going to put numbers on the x-axis. If my derivative does that, it crosses the x-axis how many times? 2. Right here and right here. All right? So that x-coordinate there would be a critical number, wouldn't it? The x-coordinate right there would also be a critical number, wouldn't it? Okay? Now, to the left of that first critical number, what's the sign of our derivative? Positive. Therefore, what's f doing? Increasing. Between the critical numbers, let me change the colors to make it easier. Between the critical numbers, so they're in red, what's the sign of f prime? Negative. Therefore, what's f doing? Decreasing. Back to the right of that last critical number. What's the sign of f prime? Positive. Therefore, what's f doing? Increasing again. Okay? Right here on this purple critical number, the derivative changed from positive to negative. So, on f, what happened? F has a relative what when the derivative changed from positive to negative? Max. On this second critical number, the green one, the derivative changed from negative to positive. So f has a relative minimum. There. Does that make sense? Now you got to remember it. Does it make sense? All right. It really needs to make sense. Okay? No, no, no. That's not a graph of the function. That's a graph of the derivative. Okay? That's the whole key. That's what I'm trying to get you to see. This is not a graph of f. This is a graph. If I can put that. That's a graph of f prime. So whenever f prime is above the x-axis, f prime is positive. Whenever f prime is positive, f is increasing. Whenever f prime is below the x-axis, f prime is negative. Whenever f prime is negative, f is decreasing. Does that help? All right, that's the way I needed to say it, isn't it? Okay, I'll say it again because I like that. That made sense to me at least. Whenever f prime is above the x-axis, that means f prime is positive. Whenever f prime is positive, f is increasing. Whenever f prime is below the x-axis, that means f prime is negative. Whenever f prime is negative, that means f is decreasing. Where the derivative changes from positive to negative, you will have a relative maximum for f, not for f prime, for f. Whenever the derivative changes from negative to positive, f will have a relative minimum at that point. Does that help? Okay, good. Yeah. If that was f, yes, but that's not f, that's f prime. For us, at this point, it doesn't matter. Once we get to concavity of functions, then it'll come back into play, okay? We'll do one of those in a minute. Julie? Yeah. All right, y'all with me? Could I make a rough sketch of f from this information? I can. Okay. Now, it's going to be rough, but let's see, I'll use black. F is increasing, and then it's decreasing, and then it's increasing. Now, where on, and of course this didn't all join together, now where on the coordinate plane is this occurring? I have no idea. Maybe it's all taking place down here. Maybe it's taking place up here. I don't know. But is it wider or narrower, the graph? I don't know. But I do know the increasing, the decreasing, the increase. I know that for a fact. Okay? Now look, I can't do this. You looking? I can't shift it over like that, can I? I can shift it up or down. I can make it wider. I can make it narrower. Because I don't know. They didn't give me enough information to know any better than that. But I do know that it's going up, then it's going down, then it's going back up. I know that for a fact. No, I'm not finding the max and min of f prime. No, I'm finding the max and the min of f. I'm using f prime to do it. I'm not finding the maxima or minima of f prime. I'm using what? Yes. whenever f prime is negative and f is decreasing. Look, even if the y coordinates are in the millions, right? Okay, we get so tied up about what's going on around the x-axis because that's where positive and negative happen, right? So the f prime is going to be near the x-axis. That doesn't mean f is. F could have y coordinates in the millions, or f could have y coordinates in the negative trillion. I don't know. Okay? All right, let's do another example. Let's do number 68. Similar but completely different. In that, we still don't know the equations. Okay? We always feel safer when we know the equations because we're pretty good at math, right? We're pretty good at algebra. We feel like we can crunch it out. You got to be able to do these problems without equations. Because like I told you before, this is where the AP people find out if you understand the concepts without asking you about any algebra. Okay? I had one person that's unfortunately kind of a higher up in the deal that just flat out said to me, high school students suck at algebra. And I'm a little offended by that because we don't. Okay? But they're going to ask you questions without you using algebra. It all depends then, not have I memorized what Mr. Jackson told me to do to work the problem like this. Do I really understand the relationship between the sign of f prime and the direction of f? Okay? So, in exercises 65 through 7, assume that f is differentiable to all x. So, the derivative never not exists. Okay? We can have f prime of x equals 0. We're never going to have f prime of x does not exist on it. The signs of f prime are as follows. F prime of x is greater than 0 on the interval from negative infinity to negative 4. All right? I like to think f prime positive. I just have an easier time of remembering it in my head if I'm thinking positive instead of greater than 0. F prime of x is less than 0 on the interval from negative 4 to 6. So that means f prime is negative on that interval. And then f prime of x is greater than 0 on the interval from 6 to infinity. That means f prime is positive again. Now, I'm not even going to read the question yet. You need to understand the following thing, whether it comes into play on this particular question or not. On that interval there, where f prime is positive, what's f doing? Increasing. On the interval here where f prime is negative, what's f doing? Decreasing. On the interval here where f prime is positive again, what's f doing? It's increasing. Okay? All right. Now we'll answer their questions. You need to know that because you need to know that, whether it comes into play on this particular question or not. Okay? All right. Supply the appropriate inequality for the indicated value of c. They tell us that g of x equals negative f of x. And they tell us that we're supposed to compare g prime of 0 to 0. So our answer is going to be g prime of 0 is greater than 0 or g prime of 0 is less than 0. That's what we're going to end up with. Okay? G prime. They didn't tell us g prime. We got to find it ourselves. So g of x equals negative f of x. If I want g prime of 0, I need g prime of x first, don't I? Because g prime of 0 just means the value of g prime of x when x equals 0. So I need to find g prime of x. Okay, take the derivative. What's the derivative of g of x? G prime. What is it? It's g prime of x. Now I'm not uncovering this yet. I will. G prime of x equals. Now, on the right side, use the constant multiple rule. that negative in front of f of x is like a negative 1, right? So the constant multiple rule says the derivative of that will be negative 1 times whatever the derivative of f of x is. What can we call the derivative of f of x? F prime of x. So we figured out our own little selves that g prime of x equals negative f prime of x. Now, that negative sign really means opposite, doesn't it? G prime and f prime have opposite signs, don't they? If f prime is a positive number and there's a negative sign in front of it, then g prime is going to equal a negative number, isn't it? If f prime is a negative number, but it has a negative sign in front of it, won't that make g prime a positive number? So f prime and g prime have opposite signs. Okay? Now, let me do this. All right, so let's substitute a 0 in there. Make that g prime of 0. So g prime of 0 has to equal negative f prime of 0, doesn't it? And how do we find f prime of 0? We go back up here to this chart. Which interval contains 0? Second one. Okay? So on that second interval, f prime is negative. So f prime of 0 is a negative number. Well, negative times negative means that it's positive, doesn't it? Or like I said before, g prime and f prime have opposite signs. So since f prime is negative when x equals 0, g prime must be positive when x equals 0. Well, if g prime is a positive number, if g prime of 0 is a positive number, is it less than 0 or greater than 0? Greater than 0. So our final answer is g prime of 0 is greater than 0. They're expecting you to figure things out without knowing an equation. Uh-huh. They gave us that negative. We look up here and we see that f prime is negative whenever x equals 0. So I've got a negative number times some other negative number. I don't know what it is, but I do know that negative times negative is positive. Because it's positive. If g prime of 0 is equal to a positive number, then g prime of 0 is greater than 0. Exactly. Okay? Y'all with me? All right. Let's see. I'll come back to that. No, don't do that. I didn't mean it. Let's take a look at number 60 that you worked on yesterday. I don't want you to get distracted by the other ones. So, number 60. We're given in the book that F has this graph. and we're supposed to graph f prime. All right, the directions say the graph of f is shown in the figure. Sketch a graph of the derivative of f. Okay? All right. So, we look at f. We start over here at negative infinity. So, we're moving along here. Is f increasing or decreasing? It's increasing. If f is increasing, what's the sign of f prime? Positive. So I know for a fact that f prime's up here somewhere, don't I? I know that. Okay? So let's keep following f until it's no longer, well, let me rephrase that. Where can weird things happen on graphs? Where do graphs change directions? Critical numbers. And critical numbers, that's where derivatives can change signs, right? So critical numbers are important. They may give us something really important like a max or a min. They may end up just really not being nothing. Not being nothing. They may end up being nothing. Yeah, I thought I was in Graves County there. Did I say that out loud? I meant, okay. So F is increasing, increasing, increasing. Hey, it keeps on increasing, doesn't it? But something weird does happen right there. F has a vertical tangent line right there. Now, it's not going to give us a max or a min because F doesn't change directions. It really doesn't. Okay? But what's the slope of a vertical line? Undefined. Okay, so the derivative doesn't exist right there. On the y-axis, the derivative doesn't exist. And then the function just keeps increasing. And I know it kind of levels off the way I drew it, but even though it's going sideways a lot faster than it's going up now, it's still going up, isn't it? Okay? All right, so since f is always increasing, that means f prime's always positive. F prime's up here somewhere, okay? So let's sketch a graph of it. Now, let's think about slopes of tangent lines. If I'm over here, the slope of that tangent line's really flat. That slope's not very big. A little bit bigger, sloped up a little bit more, sloped up a lot more here, sloped up really fast here, isn't it? So that's how come I said the derivative probably looks something like that. It's always positive. It's really small on the far left because the slope's really small. And then as we get closer to that vertical tangent line, the derivative's getting bigger and bigger and bigger, isn't it? The slopes of those tangent lines are getting really large before that becomes a vertical tangent line. That's why I have a gap. Derivative does not exist on the y-axis. When x equals 0, the derivative doesn't exist. So look at tangent lines again. All right, I would have a pretty steep slope there, and then it really levels off and gets smaller and smaller slopes, doesn't it? So I start with a really big slope, and it levels off and gets smaller and smaller and smaller. It always stays positive, doesn't it? Okay? Now, so there's F. There's F prime. Yeah. You mean the vertical tangent line? Okay. All right, here's what we would say. We would say that we have that, and here's where there's there's a little bit of disagreement among calculus people, all right? Because some people would say that you must state that f is increasing from negative infinity to 0, and then again from 0 to infinity. All right? Others would say, since it's a single point and it never changes direction, it's okay to say that it's always increasing. I'm in that camp. I would say it's always increasing because there wasn't a maximum or a minimum at 0 when x equals 0. It's just a single point. When all you're looking at is one point, you can't tell what a graph's doing anyway. You got to have an interval for something to be increasing or decreasing. So I'm in the camp of f is increasing from negative infinity to infinity. That's the x-coordinates. Negative infinity just means start over here on the left. Okay? All right. What else would you like to see from the work you've already done? 73. All right, on 73. The function f is differentiable on the interval from negative 1 to 1. The table shows the values of f prime for selected values of x. Sketch the graph of f, approximate the critical numbers, and identify the relative extrema. So they give us this table. They give us those x values, negative 1, negative 0.75, negative 0.5, and so forth, up to 1. They even give us the values of f prime. Not values of f, those are values of f prime. Okay? Now, they want us to sketch the graph of f. They want us to approximate the critical numbers and tell where we have relative extrema. So let's go a little bit at a time here. If we're going to sketch a graph of f, we need to remember when the derivative is negative, f is decreasing. When the derivative is positive, f is increasing. So where the derivative is negative, f's decreasing for all that in yellow. And then the derivative is positive, so f's increasing there. Derivative negative, f is decreasing again. So this isn't my final sketch, but decreasing, increasing, decreasing. That's what's going on, isn't it? Okay? Now, we know that f changes. We know that f prime changes from negative to positive right in there. We know that f prime changes from positive to negative right in there. That means f changes from decreasing to increasing at that first little red mark I put, and then it changes from increasing to decreasing at the second little red mark I put. How come? Because f prime, no, that's not positive there. Because f prime is negative there, f prime is positive there, f prime is negative there. So, where f prime changes from negative to positive, does that give us a relative max or a relative min? Min. So we know there's a relative minimum somewhere between these two x-coordinates, don't we? Do we know where? Nope. Somewhere between them, there's a relative minimum. All right? When f prime changes from positive to negative, do we have a relative max or a relative min? Relative max. Somewhere between those two x-coordinates. Do we know where? Nope. Just somewhere between those two. So, we can state beyond a shadow of a doubt that f has a relative minimum on the interval from negative 0.5 to negative 0.25. We can state beyond a shadow of a doubt that f has a relative maximum on the interval from 0.25 to 0.5. I can't narrow it down any more than that, can I? Okay? All right, hang on. So, just put that on a coordinate plane somewhere. And, you know, technically speaking here, I know I can, right there's my relative minimum. So I need to have negative 0.5 to the left of it, negative 0.25 to the right of it. There's my maximum. So I need to have 0.25 to the left of it and 0.5 to the right of it. But that's the best I can do. Hang on. All right. Make sense? Okay. Are you getting the idea? You're going to have to be able to work with things without knowing the equation. Yeah. And see, that's the thing, because, look, if I give you 5 problems with the equation, where you find the derivative, find the critical numbers, make your first derivative test, and come to a conclusion. And then I give you 5 problems where you don't know the equation. The ones where you do know the equation require a lot more paper and a lot more time. So you end up thinking, well, they must be more important. Not necessarily. Okay? Not necessarily. All right, was it 13 next and then 8? All right, 13. Right, on 13, we're supposed to identify the open intervals on which the function is increasing or decreasing, and let's go ahead and find those maxes and mins as well. So, 13, and I'll just let you look at it instead of talking you through every step. Find the derivative, get the derivative written as one fraction, then find the critical numbers. Critical numbers occur when, in this case, y prime equals 0 or y prime does not exist. If y prime equals 0, set the numerator equal to 0. If y prime does not exist, set the denominator equal to 0. So you get a bunch of options. But beware. So listen to me right here instead of writing. The square root of 16 minus x squared doesn't exist everywhere, does it? Because you have to have 0 or positive under a square root sign. All right? So the domain of this function, going back up to up here, the domain of the function, they didn't restrict it. They didn't tell us it's restricted, but it is, isn't it? If x is a number bigger than 4 and I square it, 16 minus that number that was bigger than 4 that I squared would give me a negative number. So anything bigger than 4 is not in the domain of this function. Same thing for anything less than negative 4. You take a number less than negative 4 and square it, you get a number bigger than 16. You would get negative again. So they never told us. We're supposed to notice, and you're not going to, okay? There's almost no way you were going to notice that last night. But now you got something to think about. You got to notice that the domain's got to be from negative 4 to 4. In addition, you need to notice, well, so look, that changes our first derivative test. So instead of in addition, let me just say it this way. That changes our first derivative test. Almost every time, don't we start at negative infinity and then go to that first critical number? But all the numbers less than -4 aren't in the domain, so don't start at negative infinity. You got to start at 4. And at the end, on the last interval, don't go to infinity because all the numbers bigger than 4 aren't in the domain. You got to stop at 4. So you may very well have set up your first derivative test with the first interval going from negative infinity to -4, and your last interval going from 4 to infinity. You don't need those. You can't use those because the function doesn't even exist from negative infinity to -4 or from 4 to infinity. And like I said, there's no way you were going to notice that last night. You were too worried about all the new stuff, right? So that's okay. I would have messed that up too. But now that you see that, it actually makes it easier when you notice that, doesn't it? Because you were getting some weird stuff going on those intervals where the function doesn't even exist. At least you should have been getting some weird stuff going on. Well, because when the derivative equals 0, how can a fraction equal 0? When the numerator equals 0. So y prime equals 0 means the numerator equals 0. Y prime does not exist means the denominator equals 0. Lot to remember, I know. But just because it's a lot to remember doesn't mean I don't expect you to remember it, because I do. All right, let's take a look at number 8 real quick. You can come back and watch the video if you want to get all the rest of that. See how I'm lingering on that? So you can hit pause, get the rest of that. Number 8. All right, on number 8, you'll have to look in your book to get the graph. But they give us a graph, and they say to identify the open intervals in which the function is increasing or decreasing. Well, the graph looks something like that. That's a really bad drawing. But there was the y-axis, there was the x-axis, something like that. So that function's always decreasing, isn't it? Okay? So, for as long as it exists, and I can tell, well, they tell me in the directions. They restrict the domain like this. They say 0 is less than x is less than 2 pi. For that entire graph, then, the function's decreasing. So for that entire graph, what's the sign of the derivative? Negative. Okay? All right. I think we will stop there.